All right, welcome back to the Solid series. Today, we are diving into the principle with, let's be honest, the scariest name of all, the Liskov Substitution Principle. I know, it sounds super academic, right? Like something you'd find buried in a textbook, but stick with me, because I promised, by the end of this, it's going to feel totally intuitive. So let's start with this quote from Robert C. Martin. He talks about fragility. And you know exactly what he means. It's that horrible feeling when you make one tiny, perfectly reasonable change over here, and then the whole system just implodes in a place that has nothing to do with what you just touched. It's maddening. Well, the Liskov principle, that's our secret weapon to stop this kind of chaos. It's all about making sure our code isn't lying. Okay, here's what we're going to cover. First, we'll tackle why this thing sounds so scary. Then, we'll get into the classic a square is a rectangle problem and see a really surprising test failure. After that, we'll break down what Liskov's principle actually is, talk about the ripple effect of getting it wrong, and wrap it all up with a simple duck test to make it unforgettable. Let's get into it. All right, first up, the scariest solid principle. Let's just go ahead and tackle the L in solid. Seriously, don't let that name intimidate you. The idea behind it is actually something you deal with every single day. You just don't call it, well, that. So let's use an analogy. Think about a universal TV remote. It's designed with a basic set of expectations, right? A power button, volume controls, channel buttons. It expects to talk to a television. Okay, so your remote expects any television to have some basic functions. On, off, change channel. Now, you go out and buy a fancy new smart TV, and hey, a smart TV is a television, right? But what happens if you point your trusty universal remote at it, press change channel, and the whole TV just crashes? Well, that smart TV might be a television, but it's a really bad substitute for one. It broke the remote's expectations. That's the core idea right there. Now, let's dig into the most classic example of this, a real rite of passage for programmers, the square and rectangle problem. On the surface, this seems totally logical. Of course a square is a rectangle. But as we're about to find out, what makes sense in geometry can cause some serious headaches in our code. So check this out. On the left, we've got our rectangle class. Super simple. It's got a width and a set height method. No big deal. Then on the right, we make a square class, and we say it inherits from rectangle. This feels right, doesn't it? A square is a rectangle. But here's the catch. To keep it a perfect square, if you change the width, you've got to change the height to match, right? And same thing the other way around. That little detail is going to be important. Okay, so this is where the fun begins. Let's see what happens when somebody actually tries to use these classes. We're going to write a little test that only knows about rectangles and see how it handles our new square. Here's our test code. It's dead simple. It takes any object that's a rectangle, sets the width to 5, sets the height to 10, and then it checks. Does the area equal 50? Of course it does. 5 times 10 is 50. This can't possibly fail, can it? And yep, if we give it a regular rectangle object, everything is fine. Width becomes 5, height becomes 10, the area is 50. The test passes, exactly what we'd expect. But watch this. The moment we substitute in our square, bam, the test fails. The area is 100, not 50. So what the heck just happened? Well, think about it. The test called setHeight10, and our special square class, trying to be helpful, said, oh, if the height is 10, the width must also be 10. So the area became 10 times 10. The fundamental assumption of the test was shattered. And this is the part that messes with everyone's head. You're sitting there thinking, but a square is a rectangle. My whole life I've known this to be true. But our code is screaming at us that no, actually, for its purposes, a square is a terrible rectangle. And this right here, this is the entire reason the Liskov substitution principle exists. Okay, so let's finally put a name to the rule our poor square class just broke so spectacularly. So here it is, the official academic definition. If for each object O1 of type S, there's an object O2 of type T, yeah, okay, that is a lot. It's technically correct, but let's be real, you're not going to remember that when you're coding. So let's just boil it all down to this. In simple terms, a subclass must be substitutable for its parent without breaking anything. That's it. Any code that was written to work with a rectangle should work perfectly with a square without even knowing it's a square. If it can't, you have a problem. And this is the story of what went wrong in 3 acts. 1, the parent, rectangle, made a silent promise. set width and set height don't affect each other. 2. The subclass, square, betrayed that promise. It secretly linked them together. And 3. The client, our little test function, got a huge, unwelcome surprise and the whole thing broke. Right now, you might be thinking, okay, that's a cute little puzzle, but does it really matter? And the answer is, oh, yeah, it absolutely matters. This isn't just some academic exercise. Violating this principle is how you get those brittle, nightmarish code bases we all hate. Because look what happens. You get a bug, so what do? You start writing horrible code like, if this thing is a square, then do this special calculation. And now your code is littered with these checks. That totally kills polymorphism, which is the whole point of using inheritance in the first place. And remember the open/close principle? Well, you just violated that too, because now you have to change this code every time a new weird shape comes along. Your beautiful design just turned into a rigid, fragile mess. So, how do we avoid all this pain without having to recite that crazy formal definition? Well, thankfully, there's a much, much easier way to remember this. It's called the duck test, and I love this quote. If it looks like a duck, quacks like a duck, but needs batteries, you probably have the wrong abstraction. It's perfect, right? Your square looked like a rectangle, it inherited from a rectangle, but it behaved in a surprising way. It needed batteries. Its behavior didn't match the expectation. It's not about what something is, it's about what it does. And that really is the entire point. When your class inherits from another, it's making a promise. It's signing a contract that says, I will behave just like my parent. You can trust me. Your job is to make sure your subclasses aren't liars. And trust me, this principle is the source of some of the most confusing, pull-your-hair-out bugs you'll ever find. So I gotta ask you, what's the craziest bug you've ever chased that turned out to be because of bad inheritance like this? Drop your war stories in the comments. I'd love to read them. All right, next time, we're tackling the I in Solid, the interface segregation principle. We're gonna talk about why making your classes implement methods they don't even need is such a bad idea. Make sure you're subscribed so you don't miss it. See you in the next one.